For centuries, humans have dreamt of creating machines that can think. This dream has been a part of our collective imagination, inspiring countless stories, myths, and legends throughout history. From the earliest days of civilization, people have envisioned mechanical beings that could perform tasks, solve problems, and even possess a form of consciousness. These artificial minds have populated our myths and stories, serving as both a source of wonder and a cautionary tale. In ancient Greek mythology, the god Hephaestus created mechanical servants, while in Jewish folklore, the golem was a clay figure brought to life through mystical means. From ancient golems to Mary Shelley's Frankenstein, the idea of creating life through artificial means has always fascinated humanity. Frankenstein's monster, a creation of science gone awry, reflects our fears and hopes about the potential of artificial beings. But it wasn't until the mid-20th century that the dream of artificial intelligence began to take a more concrete shape. The rapid advancements in technology during this period laid the groundwork for the development of machines that could perform complex calculations and tasks. In 1950, British mathematician Alan Turing posed a question that would come to define the field, "Can machines think?" Turing's groundbreaking work in computer science and his visionary ideas about machine intelligence set the stage for future developments in AI. Turing's question was not just a philosophical one, it challenged the scientific community to explore the boundaries of what machines could achieve. His work laid the foundation for the field of artificial intelligence, pushing researchers to consider the possibilities of creating truly intelligent machines. He proposed a practical test, now known as the Turing test, to assess a machine's ability to exhibit intelligent behavior indistinguishable from that of a human. The Turing test became a benchmark for evaluating the progress of AI, challenging researchers to create machines that could convincingly mimic human thought and conversation. The test, which involves a human evaluator engaging in blind conversations with both a human and a machine, has become a benchmark in the quest for artificial intelligence. If the evaluator cannot reliably distinguish between the human and the machine is said to have passed the test. The birth of AI as a field of study is often attributed to a 1956 workshop at Dartmouth College, a pivotal event that brought together some of the brightest minds of the time. It was at this workshop that the term artificial intelligence was coined, marking the official beginning of AI as a distinct field of research. The workshop was a melting pot of ideas, where experts from various disciplines came together to share their visions and lay the groundwork for future AI research. The workshop brought together leading researchers in computer science, mathematics, and psychology who shared a common goal: to create machines that could simulate human intelligence. This collaborative effort was driven by a shared belief in the potential of AI to revolutionize various fields and improve human life. This early optimism was fueled by the rapid advancements in computing technology at the time. The development of more powerful and efficient computers opened up new possibilities for AI research, allowing scientists to tackle increasingly complex problems. Researchers believed that with enough computing power and clever programming, they could create machines that could reason, learn, and solve problems just like humans. This belief drove the early pioneers of AI to push the boundaries of what was possible, setting the stage for the incredible advancements we see today. Alan Turing's contributions to the field of artificial intelligence extend far beyond his famous test. His work laid the groundwork for the entire field of computer science and has influenced countless areas of research and development. His 1936 paper on the Turing machine, a theoretical device that could perform any computation that could be described by an algorithm, laid the foundation for modern computer science. This concept was revolutionary at the time and has since become a cornerstone of the field. Turing recognized that intelligence at its core might be a form of computation. He saw the potential for machines to perform tasks that were previously thought to require human intelligence. He believed that any process that could be broken down into a series of logical steps could, in principle, be performed by a machine. This idea was groundbreaking and opened up new possibilities for the development of artificial intelligence. This insight was profound, suggesting that human thought, for all its complexity, might be replicable in a machine. It challenged the traditional views of intelligence and cognition. The Turing test itself was a thought experiment designed to sidestep the philosophical quagmire of defining consciousness. Turing proposed a practical approach to understanding machine intelligence. Instead of asking whether a machine could think in the same way a human does, Turing proposed a more pragmatic approach. If a machine could converse with a human in a way that was indistinguishable from another human, then for all practical purposes it could be said to be thinking. This idea has had a lasting impact on the field of artificial intelligence and continues to be a topic of debate and discussion. While the Turing test has been influential, it is not without its critics. Some argue that it is too simplistic and does not capture the full range of human intelligence. Some argue that it focuses too narrowly on language and behavior, neglecting other aspects of intelligence such as creativity, emotional intelligence, and common sense. Despite these criticisms, the Turing test remains a significant milestone in the history of artificial intelligence. Turing's work has inspired generations of researchers and continues to influence the development of new technologies. His ideas have paved the way for advancements in machine learning, natural language processing, and robotics. As we move forward into an increasingly digital and automated world, the principles laid out by Turing will continue to guide us. His vision of machines that can think and learn is becoming a reality, and his legacy lives on in the technologies we use every day. Alan Turing's contributions to artificial intelligence and computer science are immeasurable. His work has not only shaped the field, but has also changed the way we think about intelligence and the potential of machines. As we continue to explore the possibilities of artificial intelligence, we owe a great debt to Turing's pioneering work. His ideas will continue to inspire and challenge us as we push the boundaries of what machines can do. The early years of AI research were marked by excitement and rapid progress. However, by the 1970s, the field had hit a roadblock. The initial optimism gave way to a period of disillusionment and reduced funding, known as the AI winter. One reason for this downturn was the limitations of the available computing power. Early AI systems were built on rules-based programming, relying on explicit instructions to perform tasks. These systems struggled to handle the complexity and ambiguity of real-world problems. Another challenge was the difficulty of representing knowledge in a way that machines could understand and reason about. Common sense knowledge, which humans take for granted, proved surprisingly difficult to encode in a computer program. The AI winter had a profound impact on the field. Research funding dried up and many researchers moved on to other areas of computer science. However, despite the setbacks, some researchers continued to make progress, laying the groundwork for the breakthroughs that would come later. Section 4, the data revolution fueling AI's rise. In the late 1990s and early 2000s, the field of artificial intelligence experienced a resurgence. This period marked a significant turning point as researchers and technologists began to revisit and refine concepts that had been around for decades. The renewed interest was not just a fleeting trend, but a substantial shift driven by several key factors. This revival was driven by a confluence of factors, most notably the exponential growth of data and the development of more powerful computing hardware. The sheer volume of data being generated was unprecedented, and it opened up new possibilities for analysis and insight. Researchers now had access to vast amounts of information that could be used to train and refine AI models. The rise of the internet and the proliferation of digital devices led to an explosion of data. Every click, every search, every social media post contributed to a growing ocean of digital information. This data was not just abundant, but also diverse, encompassing text, images, videos, and more. It provided a rich tapestry of information that AI systems could learn from. This vast trove of information provided the raw material for a new approach to AI machine learning. Unlike traditional AI methods that relied on explicit programming and predefined rules, machine learning algorithms could learn directly from data. They could identify patterns, make predictions, and even improve over time as they were exposed to more information. Unlike traditional rule-based systems, machine learning algorithms could learn from data, identifying patterns and making predictions without explicit programming. This ability to learn and adapt made machine learning incredibly powerful and versatile. It could be applied to a wide range of tasks, from recognizing speech and images to predicting market trends and personalizing recommendations. At the same time, advances in computer hardware, particularly the development of graphics processing units, or GPUs, provided the computational horsepower needed to train these data-hungry algorithms. GPUs, with their ability to perform many calculations simultaneously, were ideally suited for the parallel processing tasks required by machine learning. GPUs, originally designed for rendering graphics in video games, proved to be remarkably well suited for the parallel processing tasks involved in machine learning. Their architecture allowed for efficient handling of the large-scale computations needed to train complex AI models. This serendipitous alignment of technology and need accelerated the progress of AI research. These developments ushered in a new era of AI research, leading to breakthroughs in areas such as image recognition, natural language processing, and game playing. AI systems began to achieve superhuman performance in tasks that were once thought to be the exclusive domain of human intelligence. This era laid the foundation for the AI-driven world we are beginning to see today, where intelligent systems are becoming an integral part of our daily lives. Section 5: AI in our midst, from recommendations to robotics.